Okay, chapter 13, the last branch of physics that we will cover in this class, thermodynamics. And right away, we will discuss one of the main parameters for thermodynamics, the temperature. It turns out the temperature shows the amount of motion in the system. Uh, the larger the temperature, the more uh, motion of atoms and molecules that make up an object. So essentially, temperature becomes the kinetic energy, and that's why you see the kinetic theory as the second part of the chapter 13. So once you understand what temperature is, you understand the kinetic energy of a thermodynamic system. Be careful with terms. It's temperature versus thermal energy. It's not the same thing. We have temperature for one thing and thermal energy for the other. Idea, be careful, do not mix them, and uh, be careful when you call something temperature and thermal energy. Um, just unit-wise, just to give you an idea right away, temperature is in Kelvin, degrees Kelvin, and thermal energy, that's energy, those are joules, so not the same units. And for the molecular kinetic theory, you have to understand that everything is made of atoms and molecules, and those atoms are in continuous, chaotic, or you say random motion. And this motion will be described by temperature and specifically uh, kinetic energy that temperature represents. How do we know that this theory is a good theory? Well, it's chemistry. Chemical reactions show evidence for the idea that everything is made of atoms. And for chemistry, the chemists, they like atomic and molecular masses rather than just mass like we used to in physics. So if you see unified atomic mass units, the U for short, then you have to convert from those units to System International. Once again, it's still the kilogram that we going to use for all the calculations in terms of physics. But if U's are given, then you have to convert from unified atomic mass units into kilograms, and you can see the conversion factor represents a very, very small number, which is fine because we're talking atoms and molecules. They're very small. It's hard to see those. For your reference, if you'll take a closer look at the periodic table of elements, you'll find the element carbon, and you'll see the number 12 next to it. That's the 12 that I mean for the molecular mass. So periodic table of elements has the mass in those units, and then you have to convert to kilograms if you want to do some calculations in physics. So we discussed solids, and then we continued with fluids, which represent liquid and gas. You can see the difference between the arrangements of atoms in solids versus liquids and gases. You can see that gases are easily compressible. This is your main difference between a gas and liquid. And for solids, we consider that incompressible. So you can't compress that in our ideal gas model. So temperature and thermometers. Thermometers allow us to measure the temperatures, so capital T. Remember, we use capital T for the period in periodic motion, and this has nothing to do with that, of course. So this capital T is your temperature, and you can relate that to your sense of hot and cold, of course. But once again, we will prove through our understanding of laws of physics that temperature is just the measure of kinetic energy for all the atoms and molecules that make up a certain object. And what's also is important is that when temperature increases, you expect some expansion. An object will expand in size when its temperature increases, and vice versa. If temperature drops, then there is a change in volume. And also, you can see that electric properties, specifically electric resistance, depends on temperature, and even the wavelength of a certain electromagnetic radiation also depends on temperature. So with change in color, you have change in that wavelength, and the color by itself is just a property of for the certain temperature. If it's red hot, that means it's certain temperature. If it's white hot, I'm pretty sure you've heard red hot versus white hot, and that color change actually represents the change in temperature as well. So in astronomy, you point a telescope towards a certain star, and you can register different colors. Say stars, some stars are blue, some stars are red, and blue stars would be hotter than the red ones. So color corresponds to temperature right away. And we measure thermometers, or measure temperature with thermometers, and all sorts of thermometers are possible. For this class, you only have to be familiar with liquid and glass type that you've seen probably at least once in your lifetime, when a glass tube is filled with some kind of a substance, usually mercury, and it's a different color, so you can tell the value inside right away. And once you heat it up, the mercury expands and the level rises to a certain level that you can read through the thermometer and tell the temperature right away. Or you can think bimetallic strip that you often see on grills, and the arrow shows the amount in Fahrenheit usually. Well, first of all, forget Fahrenheit. There's no Fahrenheit for physics or any science. It's always the Kelvin, and we'll discuss Kelvin a little later. And how do we have that transformation in terms of what's inside? Well, it is the bending of a bimetallic strip that we have inside, and you heat up the strip and see how two metals are sitting side by side, and they have different properties in terms of temperature change for them. And one, let's say blue part bends more than the green one, and with a certain temperature change, you can see how blue bends more and red bends a little less. So overall, there is a reaction of the system to the change in temperature, and you see the bending of those strips because of change in temperature. So back to units. See how it's not Fahrenheit, it's not the Celsius. Well, yeah, we have conversion between Celsius and Fahrenheit, but the ultimate result for temperature should be Kelvin. If you see something in a physics problem that is not Kelvin, you have to convert to Kelvin, like we did the other conversions to System International Units. For Fahrenheit, there's really no application. It's funny how it's still around, because Celsius scale actually makes sense. You can see the boiling point of water is 100 and freezing point for water is 0. And for Fahrenheit, there are no nice numbers to think of something that would be corresponding to, say, 100 or 0. So really, Fahrenheit scale, there's nothing good about it. For Celsius, at least you can refer that to water, which is the most common element here on Earth, and split it into 100 pieces. It's very convenient to think about temperature in that way. And from Celsius to Kelvin, you can see the conversion is very straightforward. You just add 273 to Celsius to get to Kelvin, or you subtract 273 to 173 degrees from Kelvin and you get to Celsius. So very easy and straightforward conversion. And what's good about Kelvin, there is such a thing as absolute zero. And that means at that temperature, there is no motion of molecules whatsoever. Remember, temperature represents the kinetic energy, how much motion you have inside an object that is made of atoms and molecules. So at absolute zero, there is no motion at all. And that happens when you get to negative 273 degrees in terms of Celsius. So that would be 0 Kelvin. For Fahrenheit, there is really no good connection, and the formula to convert looks somewhat ridiculous. You have to subtract 32, multiply by 5, and divide by 9. That's the conversion from Fahrenheit to Celsius. Or if you want Fahrenheit for some reason, then you multiply by 9, divide by 5, and then add 32, which is very like not convenient at all. And what you use to do the measuring of a normal body temperature, the 98, see, it's not even 100, right? There's like really no good reference to 100 degrees. 100 degrees is already fever. And for any other country that you say you're visiting, you start talking Fahrenheit and people look at you like you're crazy. Like, what kind of scale are you using? You have to subtract 32, multiply by 5, and divide by 9. This is the normal temperature that you will see on many thermometers everywhere on Earth, other than the United States. 36.7 Celsius degrees. This is your normal body temperature. This is what makes sense, at least, to me. Like, for all my life, I lived in Europe, and Celsius was the most accepted scale. Anyways, this is how you convert. And then the, once again, most important conversion is to Kelvin. You really want to convert to Kelvin at all times for all your physics calculations. It's only System International. All the formulas are for System International. And you have to add 273 to your Celsius to get to Kelvin. So if your body temperature is 36.7 in Celsius, you have to add 273 and you'll get about 310 degrees in terms of Kelvin, of course. This little diagram shows you the reference temperatures around the universe. You can see that water freezes at about, 100, 200. And then the surface of the sun is already thousands of Kelvin degrees. The center of the sun is about 10 million degrees. And the universe right after the beginning at the Big Bang stage was very, very hot and gradually cooled down to what we have as of today. You can see that today the overall universe temperature is about like 4 degrees Kelvin. Okay, let's do some calculations. And yeah, there is such a thing as zeroth law of thermodynamics. You might actually encounter that definition, because in thermodynamics there are two laws, the first and the second. But the zeroth law is just like natural, logical explanation for what is coming next. So it's not like really a law, it's just more of a logical statement that you will use for later. Say you have two objects and they're placed in thermal contact. So there is exchange in terms of energy between the two objects, eventually they will come to the same temperature. It's not going to be the temperature of the first one or the temperature of the second one. It's going to be somewhat in the middle. And once they do get to that temperature balance, we call it thermal equilibrium. Remember, for equilibrium, you think the word balance, that's exactly what's going on. So two objects will get into a thermal balance, so thermal equilibrium. This is what you expect. Say you have cold water, you have hot water, you mix them in the same bucket. Eventually, there will be a bucket of warm water, right? It's not going to be cold, it's not going to be hot. It's going to be something in the middle. So that would be the thermal equilibrium for those two buckets. So the law is, if two objects are in equilibrium, so you already have warm water, and then there is a third object that you introduce to the system, and this third object has the same temperature with, say, the second one, it follows that this third one will have the same temperature as the first one as well. If A equals B and B equals C, then C equals A. Okay, that should make sense. If A equals B and B is equal to something else, say C, then A is also equal to C. That's the logic, which is, straightforward logic. It's hard to think about something that would be equal to one thing and not equal to the other thing if the initial balance is already there. This allows you to use thermometer. It's if the thermometer shows something for one object, and then there is another object which is in balance with the previous object, then thermometer should show the same temperature for the other one as well. It's not that the temperature is going to change because you introduce a thermometer. Thermometer shows temperature for both systems. If they're in equilibrium, it's going to be the same reading for both. That's the idea behind. And as I said before, with change in temperature, there is change in volume, and even if it's just a single dimensional change, you will still be able to calculate the amount of expansion. So thermal expansion, going back to those expansion joints that you see on bridges. I'm pretty sure you notice those and you say, hey, why do we even need those? Well, if it's a hot sunny day, then the material that the bridge is made of will expand. And if there are no expansion joints, then the concrete will exert a force, like the internal force, internal stress, and that concrete would just, crack and collapse. So you don't want that, right? So you put those expansion joints and you leave a little space in between so that once there is a sunny day and there is expansion, then the joints will counterbalance for that expansion and will allow a little bit of expansion so that the bridge stays under thermal control, if you will. So extra thermal stress will not do any damage to the bridge itself. And then it's cold, so there is a cool down, and the shrinking process is implemented. So those joints will allow the bridge to contract a little bit and still stay in a stable position. So the amount of expansion is easily calculated with this little formula that I have here. So the amount of expansion depends on the material, and this alpha is just a coefficient that you can borrow from a certain table. L sub 0 is the original length, width, or the height, and delta T is your change in temperature. The more the change in temperature, the more expansion you should expect from that. And alpha is for linear expansion. You can also find beta. What is it? Yeah, right here. Beta, the same coefficient, but that would be for all 3 dimensions at once. So change in volume, when this is the original volume, and once again, delta T is temperature. Be careful, that should be in Kelvin. The delta T must already be in Kelvin. You have change in Kelvin, not Fahrenheit, not Celsius. It's always going to be Kelvin for temperature calculations. Yeah, so this diagram really has it all. This is the original length, the L sub 0. The delta L is the change, the elongation or contraction if it's the cool down process. So L is the new length or width or height. And there is a temperature change. So this was the initial temperature, now the final temperature. So you have delta. Delta is final takeaway initial as usual. So final takeaway initial. This is your alternative way of saying the same thing that you see here. You can either use delta notation or the L sub 0 notation. That's the same thing. So this one is good for liquids and gases, but for this expansion, you have to keep the pressure constant. This is somewhat a good solution for some thermodynamic processes, but this is only good when pressure is constant. And if it's not, then this is not a good enough of a connection. You have to consider the ideal gas law, which we are about to discuss. Yeah, this is the table that you can find in your textbook. Those are the coefficients of expansion. So it's either linear expansion or volume expansion. I'm pretty sure for the classroom discussion and homework, we're going to use just the linear expansion. We're going to keep it 1 dimensions. But if for some reason you need the volume expansion, then here is the table for those coefficients as well. See how it says per degrees of Celsius. It's not a good way of representing it, because delta T, once again, it should be Kelvin. It's just that the delta doesn't really matter whether it's Celsius or Kelvin. There is a 273 conversion for the initial temperature. There's 273 conversion to the final temperature. And once you do final takeaway initial, you're kind of canceling the 273 and you're left with just the change as well. So Celsius or Kelvin really doesn't matter. You will still get the same result. However, I suggest you still use the Kelvin rather than Celsius. Forget Celsius at every single step. Convert to Kelvin right away and use the Kelvin scale. That will save you from all the confusion. And once you try to calculate the efficiency of a certain thermal machine, you'll definitely make a mistake if you will not stick to Kelvin. So even though it says per Celsius degree, you still should think Kelvin. Kelvin at all times. Yeah, you can see that there is a very interesting property for water. With change in temperature comes the change in volume, and increase in temperature, increase in volume, but there is a little bit of a extra range where the properties change, and a decrease in temperature actually increases the volume. Okay, and I'm pretty sure you've noticed that if you ever left a bottle in the freezer to cool down and you forget about it, that bottle is going to explode because there will be an increase in volume, an extra stress put on the bottle, and the bottle just explodes. Same thing with water pipes in winter. If you allow the water inside a pipe to freeze, then that pipe will be under a huge stress because of the expansion in the water, and that pipe can blow up and you'll destroy the the whole system. Say for sanitation, like sewage, you definitely don't want that to freeze to the freezing temperatures. This little property has saved life on Earth through ice ages, because if you'll think about it, you remember how it was just, fish and sea life that we all come from. And those simple organisms, they were able to survive inside, say, a lake. There would be freezing of the top layer, and that top layer would expand because of this little change in volume with decreasing temperature. And that expansion would allow the ice to float on top of the liquid. Remember how ice has a little less density than actual water, so ice would float, and further cooling of the environment wouldn't freeze the lake altogether all the way to the bottom. There would always be a little bit of a liquid phase left below the ice level, and that's where all the organisms survived when it was very cold on the surface. And that's why we're still here, because if that wouldn't be the case, then the ice would just sink to the bottom and all the water would have been exposed to those freezing temperatures, and all the lakes would just be frozen, and life wouldn't be able to survive, will just freeze to death. So keep in mind that pipes need flowing water. You cannot allow that water to freeze. Otherwise, the pipes would just blow up from this expansion from 4 degrees to 0 degrees Celsius. Yeah, so pipes break when water inside them freezes. No life would have been possible, and ice cubes wouldn't float in your drink. Those are the results of this little expansion, even though the temperature is decreasing. So normally, if temperature increases, then volume increases, and vice versa, but not for water, especially from 0 to 4 degrees Celsius. Remember, we had our stresses and strains in Young's modulus for solids. Now you can think about what we call thermal stress, and the linear expansion coefficient times the linear coefficient for elasticity, and the thermal stress will produce you the same idea of stress. So it used to be stress and elasticity. Now it's the thermal stress, and E is still the Young's modulus, and alpha is what you borrow from the table. So in here, you got all different materials, so you can see how much of an expansion you get from a certain thermal stress. I have a little application problem here to show you how much of a stress we're talking about. Say concrete slabs on a sidewalk or a highway. If you'll measure them, you'll see that they're about 10 meters long. And let's say there is a change in temperature between daytime temperatures and nighttime temperatures. Say 30 degrees Kelvin is reasonable. If it's like, say, I don't know, say 60 degrees at night and 110 degrees Fahrenheit in the peak afternoon, you convert that into Kelvin and you will get about 30 degrees of a Kelvin difference. The Young's modulus for concrete is 20 times 10 to the 9th. And alpha for concrete, here we go. You can see 12 times 10 to the power of negative 6. So 12 times 10 to negative 6, that's what we have. So the amount of stress that we have inside the concrete slabs Turns out to be what? 7 million newtons per meter squared. We're talking millions of newtons. And remember Mike Tyson? It's what, 10,000 newtons that he hit for a knockdown punch. So we're talking 1,000 times more power compared to Mike. Like it's like 1,000 Mike Tysons trying to hit the concrete from within in every direction. So yeah, it's per meter squared, but still we're talking millions of newtons. So no wonder that you have those cracks inside the concrete, and the roads are eventually, destroyed by those stresses. So unfortunately, there's nothing we can do to prevent our roads from degrading from like that erosion and then eventually cracking, and then you add some snowing or some raining that also destroys the material, and eventually you have to do the repavement, do the repairs to the freeways or sidewalks. Nothing is forever. Even though it's concrete, it can withstand huge loads from huge trucks that run all over it. But with temperature stresses, it's really hard to prevent cracking, and the internal stresses are enormous. Once again, millions of newtons of forces. So you definitely need some spacers in between so that they allow the material to expand and do not get in contact between like one slab onto the other slab. And if it's cold, you have shrinking, which also does not destroy the overall freeway. Okay, as I mentioned before, this equation is good when when pressure is constant. But if pressure is not constant, then we need something else. We need a third parameter to be introduced, not just volume and temperature. And the third parameter turns out to be the pressure. Pressure, volume, and temperature. Those are three fundamental base parameters that define any thermodynamical system. You have a so-called equation of state, the physical condition of the system. And if something is changing, then you will see the change in the other parameters as well. So change the pressure, you will see how temperature and volume change. Change the temperature, then pressure and volume will change. So we will not be focusing on any process of the changes themselves. It's just the initial and the final condition that we will be looking at. And all the processes in between are definitely beyond the scope of introductory level. But if you'll go deep into thermodynamics, you will see all sorts of differential equations for the actual processes of change in between different parameters. So only the initial and the final conditions, that's what we'll be looking at. And the process of a change will just wait till we hit the equilibrium, not something in between. So for the process when temperature is held constant, you will see the connection between pressure and volume. And if pressure goes up, then volume is going down, and vice versa. Volume is going up, pressure is going down. So there's an inverse connection. An inverse connection is shown as a hyperbola. It's y equals 1 over x, if you will. So pressure is increasing, and volume is decreasing, and vice versa. You increase the volume, pressure is going to drop. So your Boyle's law is part of the ideal gas law when temperature is just held constant. So do not change the temperature. You will see how pressure and volume depend on each other. See, for temperature of 320 degrees, you go through this graph. So what do you have here? You have a higher pressure, less volume. And in here, it's lower pressure, greater volume. So if you're going downward, that's what you get. If you're going upward, so once again, greater volume, less pressure, going up, more pressure, less volume. And you can see how it's the same type of graph no matter what the temperature is. If temperature is kept constant, then pressure is inversely connected to volume. The Charles law connects volume and temperature if pressure is kept constant. And you can see that you start from absolute zero in terms of Kelvin, so negative 273 degrees Celsius. This is your 0 Kelvin. An increase in volume means increase in temperature. That's your expansion that we discussed here. Increase in temperature, increase in volume, and vice versa. If pressure is constant. If pressure is constant, that's what you get. And then Gay-Lussac's law, when you have constant volume, and then pressure and temperature also, if you have a linear connection, the more the pressure, the more the temperature. So keep that in mind every time you throw a closed glass jar into a campfire. Please do not ever do that because it's going to explode. Why will that explode? Well, because you throw in something into a campfire, temperature is going to increase. Increase in temperature, increase in pressure. So the air inside that glass jar will experience an increase in pressure. Pressure is force per area. So there will be a huge force inside the jar that will force the jar to just blow up. And your campfire will be filled with small pieces of glass that will, hurt someone. So the jar is going to explode, and you don't want that explosion. So it's not a fun prank that people will try to do around the campfire. So the more the pressure, the more the temperature, and vice versa. The less the temperature, the less the pressure. So those three laws that we just discussed, the Gay-Lussac's, the Charles and Boyle's law, combined, you see that there is connection between the three parameters, pressure, volume, and temperature. And that's exactly how the ideal gas law looks like. But see how there is not an equal sign. It's like proportional to. The product between pressure and volume is directly proportional to the temperature in Kelvin, of course. So you have to, in order to make it an equation, you have to consider the amount of gas, like how much of a gas do we have inside the system. And of course, the more the mass, the more pressure it's going to produce. So you put the mass towards the temperature, and that would be the linear connection to the pressure or the volume that it's going to take. If you have a lot of gas, if the mass is enormous, then the volume of that gas is going to be more than a small amount. So just, basic logic allows you to put the mass on the right side of the equation. And then we also have to consider what kind of gas do we have. And for that, we have to go to a definition of mole that that chemistry people use a lot. And now it is time to actually introduce. One, two. Yeah, so the headset turned off. So now we have to introduce the chemistry of the process as well. You can see that mole is the ratio between the actual mass in grams, be careful, grams, not kilograms, and the molecular mass that you find in the periodic table, grams per mole. So an example for real world calculations, say you have hydrogen, and hydrogen is made of 2 atoms, so it's 2 times whatever you see in the periodic table. There's number 1 below the hydrogen, so you multiply by 2 because there's 2 atoms in the molecule, and you get the 2 grams of the substance. And that's what you would convert to kilograms and do the physics calculations. If it's neon, then it's neon by itself. It's not neon 2, it's not neon 4. So it's just 20 is the number, and you multiply by 1, and you get 20 grams. For CO2, for complicated molecules, you have to add up everything that you have in terms of carbon and oxygen. For carbon, it's 12 units. And for oxygen, it's 16 units, but 16 has to be multiplied by 2 because its oxygen is O2. So 2 times 16. And whatever you have from carbon, that's going to give you 44. 12 plus 32, that's 44 grams. So this is your connection between the grams and the molecular mass, because you have a certain amount of moles in a certain material. The overall connection between the pressure, volume, and the temperature is shown right here. Pressure and volume on one side, temperature on the other side. And what you have also here is what we call concentration, or the number of moles. And the capital R is the universal gas constant. It's just a constant. You don't have to remember it. I'll give it to you for the test. But for all of your thermodynamics calculations, you really want to keep it handy. The 8.3, 8.31, if you want 3 sig figs, that you want to plug in here and do the calculations. It really depends on the substance that is given. So hydrogen, that's what you do. Neon and other things. You don't have to remember periodic table of elements, of course. I will give you the concentration. I'll give you a good idea of what is given in terms of chemistry, because this is not a chemistry class. You don't have to remember all the periodic table of elements. Yeah, let's do problem solving. Let's practice that and see how it works. One more abbreviation, the STP abbreviation stands for standard temperature and pressure. Standard temperature is considered 273 degrees Kelvin, which corresponds to 0 Celsius. Or you can think room temperature about, it's like 20 degrees Celsius, so it's very close to just your room temperature. And for pressure, it's 1 atmosphere. It's atmospheric pressure, which is 100,000 pascals. It's a little more than that, but once again, I allow you to ignore the 1 and 0.3, just say 100,000 pascals, and you're good with the pressure. This statement comes from chemistry. 1 mole of an ideal gas takes 22.4 liters. Remember how liters are connected to meters cubed. We discussed that in fluids, like a bottle of a certain amount of liters. We convert that to meters cubed. Go check it out if you forgot. So this is how you connect something to meters cubed, which is volume for your calculations of volume, and then the ideal gas law. So what you will be doing most of the time is the connection between pressure, volume, and the temperature before something happened to a system, and then pressure, volume, and the temperature after something has happened inside the system. And if the amount of gas does not change, which is usually the case if you don't add more gas or you don't lose any gas, then this would be your ratio to work with. Just remember that temperature is in Kelvin, pressure is in pascals, and volume is in meters cubed. Remember, system international units. And for pressure, consider absolute pressure, not the gauge pressure, not the hydrostatic pressure. You need the absolute pressure, which is the sum total of atmospheric and the hydrostatic, the rho GH. The Avogadro's number is the amount of atoms and molecules in 1 mole. You can replace the concentration as the number of atoms and molecules that you have with respect to Avogadro's number, and rewrite the equation, the PV-nRT, in this form. So instead of concentration, you just say it's the number of atoms and molecules that I have in my system with respect to Avogadro's number. Once again, Avogadro's number is a constant. You don't have to remember the actual value. I will give it to you for the test. And sometimes you will see the notation that it comes with Boltzmann's constant, the small k, Boltzmann's constant. It's the ratio between the universal gas constant and the Avogadro's constant. So this is a constant, this is a constant. So Boltzmann's constant is just a natural constant because it's a ratio of other two constants. So once again, R is the gas constant. Avogadro's number is the number of atoms and molecules in 1 mole. So K is the Boltzmann's constant. That just makes your ideal gas law look a little, easier in terms of, depending on what's given. If you don't want to convert from one constant to the other, you can use a different form of the equation. So N is concentration, which is number of atoms and molecules in your system with respect to Avogadro's number. And if you want to replace the Avogadro's number with Boltzmann's constant, then it's the gas constant divided by Avogadro's number. For the molecular interpretation of temperature, remember temperature measures the average kinetic energy of motion. Consider a large amount of atoms and molecules, and they move in random directions. And we're going to do the average of all the speeds in all directions. And consider molecules are far apart on average, so you can ignore the gravitational interaction. Of course, there is gravity between all the molecules and atoms that make up a certain system, but we neglect this gravity for our model. So molecules obey classical mechanics and interact only when colliding. So collisions are perfectly elastic. Remember, perfectly elastic collision is when kinetic energy is approximately conserved. Yes, there is a little bit of a loss, but we ignore that loss of kinetic energy in between those processes of collision. So no gravity and no loss of kinetic energy for collisions. That's the model for now. If this is the model, then let's do the calculation of the average force that atoms and molecules exert on a wall of a container. Second Newton's law says change in momentum with respect to time. And see how the change in momentum says 2mv. Why is that so? Well, if the initial velocity is to the left and final is to the right, then what is the change? Change is final take away initial, and final is your mv, positive mv to the right. And the initial was negative mv because you are moving in the opposite direction. So it's mv minus a negative mv, so you have twice the mv of a change in the momentum. And how do you calculate the time? Well, it's the distance traveled by atom and a molecule, and then it's backwards motion, so it's L and another L, so it's double the L over the speed of that motion. So 2's cancel, and you get mv squared over L for a single molecule. And of course, we have more than one molecule, so on average, let's just multiply by an average velocity, not just a certain velocity for a molecule, and multiply by the number of molecules. So if this much comes from one molecule, then multiply by capital N the number of molecules, you'll get the total force from all the molecules that hit the wall at a certain interval of time. There is a trick in statistics where you can say, okay, if it's V sub x squared, then you can do the average for all the dimensions x, y, and z by dividing by the number of dimensions. So if you have three-dimensional container, length, width, and the height, then you just take your average V squared and divide by 3. This is just a statistics trick, which actually gives a good estimate on what's the average velocity of all the atoms and molecules inside the container. So this is the force, the average force, if you will. So the pressure, which is force per area, would be all of those things divided by the area. And area is also connected to the volume. So you can see how area is multiplied by the length of the container, and that becomes the volume of the container. So on average, the pressure inside the container with a certain gas molecules moving at a certain speed, and that's the number of molecules, and that's the mass of the gas, that is connected to the volume of the container. You can multiply both sides by the volume. So multiply both sides by V. This V cancels, and V is moving to the left side. And you want to multiply by 2 on top and the bottom just to get rid of mv squared and get mv squared over 2. And I'm pretty sure you've noticed, oh, it's mv squared over 2 now. So it is what we used to call kinetic energy. Yes, there's an extra 2 at the top for the right side, but it's the 1/2 mv squared that we were looking for in the first place. So 2/3 n and the kinetic energy actually define the idea to calculate the kinetic energy of molecules in an ideal gas. So you can say PV is nKT. We had this notation derived from the Boltzmann's constant notation. K is the Boltzmann's constant. So nKT on one side, and on the other side, the product between pressure and volume is 2/3 n and the kinetic energy. So your kinetic energy, n cancels on both sides, and you're left with 3/2 and the kT. So 2/3 n equals to nKT. Solve this for the kinetic energy, and you will get 3/2 of a kT. You will hear, instead of a kT, you would hear cat a lot. It says 1.5 of a cat. The cat that say meow meow. That's a common joke between physicists that do thermodynamics. When they calculate kinetic energy of a certain gas, they consider 1.5 of a cat. So cat is here only because there is a Boltzmann's constant, and T is for the temperature in Kelvin. So kinetic energy is connected to the temperature via the Boltzmann's constant and another coefficient. So those are just coefficients, the constants. So the physics behind temperature is that it is the average kinetic energy of all the atoms and molecules that make up a certain thermodynamic system. So temperature is kinetic energy. So measuring the temperature, you're measuring the temperature of your body with a thermometer. You're technically measuring how much speed your atoms and molecules that your body is made of have right now. And when you have a fever, it's just those molecules start vibrating back and forth faster to fight against, say, a bacteria or a virus that your body has to fight against. And if you consider, say, a cup of tea, a hot tea will have atoms and molecules of water vibrating faster, and that's why it appears to be hot. It's the same tea, it's the same constant in terms of chemistry, but temperature-wise, if it's greater temperature, it means more motion of atoms and molecules that make up the actual cup of tea. Yeah, and you will also see the so-called root mean square, which is also a statistical parameter. So instead of average speed, you can actually take the radical out of that average speed squared and get the speed by itself. This speed is what you call the root mean square. So you have 3/2 of a cat that define the kinetic energy, and 1/2 mv squared is still there. Taking the radical of that average will give you the root mean square speed. Taking the radical of 3/2 cat lends you this little formula for root mean square speed. So if you want to connect to temperature, it's 3 times the Boltzmann's constant, temperature in Kelvin, and mass in kilograms. Be careful, everything is system international. Kelvin, kilograms, and if it's pressure, it's pascals, and volume is in meters cubed. Keep track of units. All the mistakes in thermodynamics that you can possibly make will probably come from you not converting to system international. Okay, question to you. Gas mixture, different types of molecules and masses decrease. M1 is greater than M2 is greater than M3. What do you say for kinetic energy? Well, it's a trick question. You might say, oh, it's 1/2 mv squared, so the more the mass, the more kinetic energy I have. But that's not the case. Kinetic energy is a measure of temperature. And what do you see here? It's for average kinetic energy, you think temperature. And if it's the same temperature for all the gases, then you will get the same kinetic energy. So answer is the same if it's the same temperature for all the gas mixtures. Be careful with, see how it's not just mass, it's also the how fast they go. The more the mass, the slower the velocity is going to be. The less the mass, then they're going to move faster. I can give you an idea that, say, atoms and molecules of helium on the sun, they move super fast. We're like talking thousands of miles per hour because the molecules are so lightweight. But if you replace them with heavier molecules, they will move not as fast. So that temperature-wise, you'll still get the same value for kinetic energy. Remember how it was, is it the moon on the earth or the earth on the moon with the force? And you say forces are the same, but mass is more, acceleration is less. Acceleration is more, mass is less. That's why for the moon, the mass is less, acceleration is more. That's why the moon goes around the earth. And for the earth, mass is more, acceleration is less, and the moon is just, and the earth is just sitting still. So for kinetic energy, you're not considering the mass and velocity, you're considering the temperature. Or the combo between the mass and velocity. Both mass and velocity. But chances are you're going to do temperature instead of all that. So look at the temperature and compare kinetic energies in terms of temperature in Kelvin. Yeah, same thing, but now it's the RMS speed. See, it was kinetic energy as a whole. Now it is just the speed. And just the speed, of course, gives temperature and then the mass. If the temperature is the same, but masses are different, the more the mass, the less the speed, the inverse connection. Like, once again, same as for the forces are the same, but mass times acceleration, can be different. Mass is more, acceleration is less. Mass is more, velocity is less. Velocity is more, mass is less. So if mass is decreasing, then speed is increasing. Oh, good news. We have reached the stuff that is out of the tests. You can see that the distribution of speeds is out, and real gases are also out. Once you decide the thermodynamics is going to be your research, you'll definitely go to real gas model, not the ideal gas model, and you can see it's not as straightforward anymore. It's not just a hyperbole. You can see that there is an area that you call liquid vapor region, and you have a different properties for fluids here. We're not talking about it in the introductory level for sure. And yeah, you got the triple point and all sorts of kinds of, the state of elements. We don't do any of that deep research here, but you will definitely go through it at the more advanced levels. I used to have humidity on my tests, not anymore, for the same reason. Like, we don't have time to go through all the thermodynamics in 3 days. So no humidity, but you're more than welcome to read through it and see how relative humidity is what you normally see in the weather forecast for your personal application stuff. Make sure that humidity inside your house is between 30 to 50%. If it's less than 30, you will suffer cracks on your skin, and it's gonna be painful. Your skin is gonna go through damage. So you need the humidifier, especially here in California. If it's very dry conditions, you need a humidifier for your normal body operation. And if it's more than 50, well, it's going to be the other way, because humidity added with heat. That's what we have on East Coast. That's why temperatures on East Coast feel not so comfortable. Say 100 degrees here versus 100 degrees on East Coast. It's a totally different 100 degrees because of humidity. Anyways, keep your humidity from 30 to 50%. That's the ideal conditions for your body to operate. And get a humidifier. That would be a benefit when it's very dry and hot outside. Yeah, the dew point is also there. Well, this would be your foggy conditions, that overcast that you see around. So a lot of applications, but once again, I am not talking about advanced thermodynamics, just the basics, just the 1/2 of a cat, the RMS speed, and consider ideal gas law that we're going to do calculations with in classroom discussion and homework problems. Okay, pausing for now. Stop recording.